In this video, we develop general necessary conditions of optimality for a continuous time optimal control problem with a free final time. In other words, we will include the final time, or the length of the time interval over which control is applied, among our optimization variables. As usual in this course, we will start with the framework of calculus of variations. We perform the optimization over smooth functions of an independent real variable x. I sketched here two functions, the red one, y star, representing the minimizer, and the white one, y, being just another function that is obtained by perturbing or varying the minimizer. Note that in contrast with the basic problem of calculus of variations, here only the left end of the interval is fixed. X is equal to a, while the right end of the interval is free and subject to optimization. The value of b that I show in the figure corresponds to the optimal function y star. Well, I should have named it b star then. Anyway, deviation or perturbation, or actually variation, that's how we call it in the calculus of variations, from the optimal function y star at a given x is labeled delta y of x. We had some discussion of this in our introductory lecture on calculus of variations. The change in the final time is labeled delta b. Here we prepare the ground for the situation in which not only the final time, but also the final state, the state at the final time, is free. The fixed final state case then follows as a special case. The standard procedure for finding the conditions under which y star is truly a minimizer is then to analyze how the cost function changes if we vary the minimizer a bit. But unlike in the basic version of the calculus of variations, here it's also the final time that is varied. This complicates the situation a bit, but there is an easy fix. We cast the final time increment delta b as proportional to some other delta x through the constant alpha, the same constant that is used to vary the function y. This turns the expression for the perturbed cost function dependent on just a single parameter, alpha. Now the rest of the procedure is straightforward. We need to identify the variation of the functional j and analyze under which conditions it vanishes. We can do it by isolating the first order term, first order in alpha, in Taylor's expansion, or equivalently by finding the derivative of j with respect to alpha, evaluated at 0, times alpha. We are now about to differentiate an integral with a variable upper limit. We can use Leibniz rule for differentiation under the integral sign for it. Look it up on your own if this is already evaporated from your memory since your undergraduate times. We get three terms. The first one, the integral, is already well familiar to us, isn't it? But the same holds for the second term. We have found this one in the literature, in the lecture in which we developed conditions for fixed interval but free value of the function at the end. What is brand new here is the third term, L evaluated at b times delta x. Now remember that we define the variation as a product of this derivative and alpha. Therefore we do the multiplication and get the variation of j. Once again, three terms. Two are already familiar. The last one, L at b times delta b, is new. Invoking the now already notoriously known fundamental theorem of calculus of variations, the first term, the integral, must vanish on its own in order for the whole variation to be 0. The reason is that the variation delta y of x is arbitrary. But then the other term under the integral sign must be identically equal to 0. And we get our old friend, Euler-Lagrange equation. The other two terms must vanish together. We get two conditions. Note that while Euler-Lagrange equation imposes some constraints throughout the interval, the latter condition imposes constraints at the right end of the interval only. Now let's have a more detailed look at what's going on around the free end. Here I add some more information into the figure. In particular, I introduce a brand new symbol, dy sub f. It stands for deviation from the optimal final state, disregarding the actual time at which the final state is reached. Note also that even though the optimal trajectory y star is only defined up to b, we use a simple linear extrapolation to define it also for the perturbed time b plus delta b. Contemplating this sketch a bit, we can come up with the following relationship among the various quantities defined at the perturbed final time b plus delta b. We can approximate the terms on the left with the first two terms of their Taylor's expansion. Then the value of y star at b appears on both sides, so we cancel it. We can also cancel the middle term delta prime times delta b because each term in this product is actually first order in alpha. Hence, the product is second order in alpha and decays faster as alpha approaches zero faster than the other terms. We are left with the following relationship between delta b, delta y at b, and dy sub f. Let's just keep delta y at b on the left-hand side. But this is the guy that appeared in the new boundary condition that we derived a minute ago, right? We substitute it to that equation. Collecting the terms with dyf and delta b, we get the ultimate form of the new boundary conditions, worth boxing. We can now specialize this major result for the situation when the final time and the final state are not related. The two expressions that are with dyf and delta b must now vanish on their own. Again, time to switch to the optimal control setting. The usual general cost function and the system model are given here. The only new circumstance is that the final time is also among the optimization variables. The augmented Lagrangian contains not only the original Lagrangian L and a term corresponding to the state equation, but also a term corresponding to the terminal cost. We've already seen this procedure before. We needed to get the phi term under the integral sign, and we did it simply by differentiating it first. Doing the total derivative with respect to time. Substituting this Lagrangian, the augmented Lagrangian, into the general prescription for a boundary condition, of course after the usual notational switch from x to t and from y to x and u, we get the boundary conditions for our optimal control problem. Now, if the state at the final time and the final time itself are independent, what's inside the two round brackets must vanish independently. And we get two boundary conditions. In fact, one stands for n equations, where n is the order of the system, while the second one is always a single scalar equation. Hence, n plus 1 equations, imposing the boundary conditions at the final time. You can perhaps recognize the first condition already, the vector one. Indeed, that's what we already used in optimal control on a fixed interval with free final state. In the LQ setting, this gave us the linear dependence between the state and the costate at the final time. Remember? Let's elaborate on the second condition a bit more. If we now assume that the terminal cost is not a function of time, that is, if its partial derivative is 0, the boundary condition turns into L minus lambda times f is equal to 0. But it cannot go unnoticed that the term on the left is nothing else than Hamiltonian function, with a minus sign, of course. So the new boundary condition corresponding to freeing the final time is that Hamiltonian must vanish at the final time. This is certainly worth remembering, a crucial finding. Let's now elaborate a bit more on the Hamiltonian. In particular, let's analyze how it evolves in time when evaluated along an optimal trajectory. That is, we want to compute its derivative with respect to time. Using the chain rule for finding derivatives of composed functions, this is what we get. Upon invoking the Hamilton canonical equations, we see that the first two terms cancel each other. The third term vanishes as dictated by the stationary equation. What remains is the partial derivative of h with respect to t. In the time-invariant case, that is, if neither the model of the system nor the cost function depend explicitly on time, the partial of h with respect to t is 0, and so is the total derivative of h. In other words, in the time-invariant case, Hamiltonian is constant for all times when evaluated along an optimal trajectory. Now we combine this striking result with what we have just learned about the final value of the Hamiltonian in the free final time case, and we conclude that Hamiltonian is 0 all the time. This is a fundamental observation indeed. Some control design techniques exploit it heavily. We know that Hamiltonian must be maximized, and we already know the maximum value. Once again, I feel obliged to warn you about the mess related to two different conventions for Hamiltonian function adopted by the control theory community. Know that while building the augmented Lagrangian, we can also include the constraints due to the dynamics of the system as f minus x dot. Remember that what we used before was actually x dot minus f. But then the boundary conditions need to be modified a bit. In fact, just some signs would change. In the time-invariant case, the boundary condition would again feature the Hamiltonian, but this time it would assume that Hamiltonian is defined as lambda plus, or L plus lambda times f. Well, you may find it useful to have the formulas here for both conventions, but choose your preferred one and stick to it. So far, we assumed that the state at the final time and the final time itself are independent. Our assignment was to bring the system to some desired final state, but the specification of that final state did not depend on the time at which the state is reached. In the next video, we are going to solve the problem of time optimal control, in which you are even penalized for bringing the system to the final state late. Still, whether the system reaches the final state sooner or later, the required final state is the same. But there are other situations in which the desired final state does depend on the time the state is reached. For example, tracking a moving target, right? Being fast, you hit the target at some place. Being slow, you hit it somewhere else, or not hit it at all. Here in this video, I will only state the full form of the boundary conditions. It's called transversality conditions. Just a single scalar condition actually on top of those n conditions corresponding to the initial states and n conditions corresponding to the final states given by the psi function. For derivation and even justification of that term transversality, have a look elsewhere, perhaps in my lecture notes on the course website. In the next video, we are going to capitalize on our pain in going through all these technical results and formulate and solve the problem of time optimal control of constrained linear systems.